Hello everyone, welcome back to the next framework in engineering. Today we're starting something huge, something I'm particularly excited about.
Today we're launching Chapter 1 of our series, the master plan to conquer Mars with SpaceX Interplanetary Engineering. If you enjoy this content, my intention is to cover all 10 consecutive launch windows, from the first test mission to the establishment of a self-sufficient city.
We're going to go step by step, window by window, unraveling the engineering behind humanity's greatest adventure. But before we dive in, I need us to keep our feet on the ground.
Everything you're going to hear today is based on real technical documentation, patents, and aerospace engineering papers. However, we need to be realistic about the current situation.
We're at a critical point right now. Cryogenic propellant transfer in orbit, the holy grail for reaching Mars, has not yet been validated.
We expect to see that critical test this summer.
Therefore, even though our hearts might want to shout 2026, engineering tells us that window is too premature for a surface landing.
So, in this video series, we've decided to rule out a surface launch in 2026. We're going to work with the most robust engineering hypothesis, the August to September 2028 window.
I hope I'm wrong. I hope SpaceX surprises us and speeds up the timeline. We hope to be proven wrong, but we want this analysis to be as real and tangible as possible.
So, set your watches because we're heading to 2028. Alright, it's August 2028. What are we launching?
We are not sending humans. I repeat, no humans in this window.
It would be technically irresponsible. The goal of this first window is Critical Architecture Validation, CAV.
The fleet consists of 3 ships. Starship, 3 pure cargo variants. No windows, no seats, no gym. They are 3 stainless steel cathedrals packed with sensors and machinery.
Why 3? In aerospace engineering, relying on a single unit is dangerous. If you send one and it fails, you've lost 2 years of data. If you send 3, you have redundancy. These 3 ships have a clear mission to demonstrate that we can land something the size of a 15-story building on a planet with an atmosphere that is 1% of Earth's. And once there, demonstrate that we can keep the systems alive.
We're going to break this down into 3 technical blocks: how we get there, who works there, and how we survive. Before Carlos tells you more, we ask you to subscribe to the channel.
That's the best way to support us in creating more content.
Thank you, Anna. I'll describe this first phase of how we get to Mars.
It's the most terrifying phase of the mission: EDL entry, descent, and landing. We're going to assume that by 2028, we've already overcome the fuel transfer phase and are capable of reigniting the engines to exit orbit and reach Mars.
Imagine you're coming in at 7.5 kilometers per second. That's hypersonic. You need to decelerate that enormous mass to a complete stop in a matter of minutes. The problem is Mars. Its atmosphere is dense enough to burn you alive due to friction, but too thin to slow you down with parachutes alone.
For this 2028 mission, Starship will use a thermal protection system
made of tiles, optimized for Mars re-entry. We've already seen test images shared by SpaceX. So far, the black hexagonal tiles have worked here on Earth. SpaceX has opted for a system primarily composed of thousands of hexagonal ceramic tiles. The tiles are made of a compound of fibrous amorphous silica. It's a low-density, refractory ceramic material that can withstand high temperatures. This approach is designed to simplify manufacturing, reduce maintenance time, and lower the overall system cost. But what if a tile breaks due to vibration? The plasma, which is superheated, ionized gas, would enter like a blowtorch and melt the steel of the structure. Bill Gerstenmaier, one of the executives at SpaceX, revealed the implementation of a new experimental material installed beneath and around the tiles, which they internally call crunch wrap. This material acts like paper. It wraps around each tile. The tiles are mechanically inserted by a robot, and this wrapping seals the gaps between them, eliminating the need for traditional gap fillers. Excess material is trimmed from the surface. Now, let's talk about aerodynamics. This is where Starship performs its famous maneuver, the belly flop. But be aware, on Mars, this is different from the tests we saw over the Pacific. The atmosphere is so thin that the maneuver happens at a much lower altitude and much higher speed.
The guidance system uses something called roll angle modulation. The ship rotates on its axis to control lift. And here, I want you to visualize an analogy. Imagine sticking your hand out of a car window at 100 kilometers per hour. If you tilt your hand, the wind pushes it up or down. That's aerodynamic control. On Earth, to feel that same force on your hand on Mars, the car would have to go 10,000 kilometers per hour. That's why Starship's flaps on Mars don't move smoothly. They have to act violently and precisely, driven by electric motors derived from the Tesla Plaid, powered by independent batteries. We can't rely on hydraulics here. Fluids at those temperatures are a headache. We've reached the moment of truth, the last 800 meters. Here, supersonic retropropulsion comes into play. We ignite 3 Raptors at sea level and shut them down one by one as speed decreases. It's a brutal braking. But where do we land? There's no pilot looking out the window. The ship could use a system called TRN, Terrain Relative Navigation. Basically, the ship has eyes, cameras, and LiDAR, which scan the ground in real time and compare it with satellite maps. If the computer sees a large rock or a slope, it has the authority to divert the ship up to 500 meters. And when we touch down, the landing gear comes into play. Forget the fixed legs from those Texas missions. These ships have self-leveling legs. Think of a professional camera tripod that adjusts itself on a rocky mountain. If one leg lands in a hole and another on a rock, linear actuators extend or retract to keep the ship perfectly vertical. This is vital. If the ship is tilted more than a couple of degrees, the cargo elevator would jam and the fuel tanks wouldn't drain properly. Verticality is survival. Thank you very much, Carlos. Now I'm going to talk about the second phase of the mission, robotics and surface deployment. All right, we've landed. The dust is settling. Now what? There are no astronauts to open the hatch. This is where the payload comes in. Each of these 3 ships carries a team of 4 Tesla Optimus humanoid robots inside. But these aren't the ones you see dancing in the demos. These are the Mars version. It's worth noting that at this point, we are being optimistic. We're going to trust Tesla's engineers to be able to develop this first version of Optimus by 2028. Many people think the problem in space is the cold, and yes, it is cold. But in a vacuum or thin atmospheres, the biggest problem for power electronics is heat. On Earth, if an engine heats up, the air cools it by convection. On Mars, there's barely any air to dissipate that heat. If an Optimus robot works hard carrying a box, its motors would cook from the inside. That's why these robots have passive radiators in their torso and liquid cooling loops. They are robots that sweat heat into space. Additionally, they have to deal with dust. Martian dust isn't like beach sand. It's electrostatic. It sticks to everything and is abrasive like diamond. All robot joints are hermetically sealed. These robots operate using a teleoperation system with a time delay from Earth. We can't control them with a joystick in real time because the signal takes 4 to 20 minutes to arrive. You can't see the robot about to fall and correct it. It would have already fallen 10 minutes ago. Therefore, we send high-level objectives. Go to point B and deploy the solar panel. The robot, using its onboard AI and the same FSD chips as cars, but radiation hardened, decides where to place its feet, how to grasp the box, and how to maintain balance. It's tactical autonomy with human strategy. What would its first mission be? Its first mission would be to deploy power. With that, we enter Phase 3. Power. Without power, the spacecraft die. They freeze. The deployment of solar panels is critical. On the International Space Station, panels deploy like a horizontal accordion. On Mars, we have 1/3 Earth's gravity and dust. That's why the engineering solution chosen for 2028 is the CTSA, Compact Telescoping Surface Array. They are vertical masts. Imagine them as ship sails that rise upwards, not sideways. Why vertical? First, because being far from the ground, they get less dirty from the dust stirred up by rovers. Second, because we use the wind to clean them. And third, because they take up less surface area. A total of about 30 square meters of solar panels could be deployed. We're talking about generating kilowatts of power. Enough for this first mission. Don't miss the next episodes, where we'll talk about a hybrid energy system with solar panels and nuclear power. That energy goes to solid-state lithium-ion battery banks. Why solid-state? Because they are denser, 500 watt-hours per kilogram, and above all, much safer. We don't want a battery fire on a planet where you can't call the firefighters. These batteries have to withstand the Martian night, power the ship's heaters, and keep the computers alive until the sun rises. Remember, in this first mission, we are validating the use of these technologies on Mars. With these results, it can be optimized for future missions. Thank you very much, Anna. I'll finish up and we'll get to the final part, and perhaps the most exciting part of this 2028 window. The validation that we can live there. Remember, there are no humans, but one of the ships will act as if there were. Inside this ship, the life support system and environmental control will be fully activated. We will pressurize the cabin to 1 Earth atmosphere, inject humidity, and simulate the breathing of 6 astronauts by injecting CO2 and synthetic chemical contaminants. The goal is to see if the filters fail, to see if Martian dust has gotten inside and is saturating the systems. It's our canary in the coal mine. If this ship maintains 1 breathable atmosphere for 2 years without failure, we will know it's safe to send people in the 4th or 5th window. And finally, the crown jewel, ISRU, In Situ Resource Utilization. We can't carry all the fuel for the return trip. We have to produce it there. In this 2028 mission, we are bringing a pilot oxygen production plant. It's a scaled-up version of the MOXIE experiment carried by the Perseverance rover, but much more powerful. We use a technology called solid oxide electrolysis, SOE. The process is pure hard chemistry. We aspirate the Martian atmosphere, which is 95% CO2, and compress it, which is difficult because the atmosphere is very thin, using special dust-resistant compressors. We heat that gas to 800 degrees Celsius and use electricity to break the CO2 molecule to separate oxygen, O2, from carbon monoxide. The goal is to produce 20 kilograms of oxygen per day. It's not enough to fill a ship yet, but it's enough to prove that the machinery doesn't degrade, that the filters don't clog, and that we can scale this up to an industrial level in the next windows, as you can see. This first 2028 window isn't a flag-planting mission. It's a foundational mission. It's laying the concrete before building the house. We are validating that we know how to brake, that we know how to deploy autonomous robots, that we can generate massive energy, and that we can breathe and manufacture fuel. It's engineering in its purest form, pragmatic, redundant, and survival-oriented. Now I ask you, do you want to see what happens next? Window 2 in 2030 is where things really get serious. We're talking about heavy infrastructure. In the next video, if you're interested, we'll analyze a fleet of 10 starships. We'll talk about complete propellant plants, industrial-scale solar farms, and the first pressurized hubs. If you want me to continue with Chapter 2 of this series, let me know in the comments. Right, we want the 2030 window. And remember, the future isn't waited for, it's designed. Until next time.